Hi, I'm Kris Kennaway, and today I'm talking about super high-res graphics. So I grew up with the 8-bit Apple II line, and that's really been my first love, especially as I've got back into the retro computing hobby. That's really where my interests have lied. I've thought a lot about the 8-bit Apple II graphics modes, and last year I wrote an image converter for double high-res, something called 2pix, which I presented at KFest last year. And then in December, I got sort of nerd sniped by 4am into seeing what could be done for the Apple IIgs graphics modes. So the result of that work was that I updated 2pix to convert super high-res images, and that's what I'll be talking about in the talk today. And this is now used in Total Replay for the box art. This was really my first real in-depth look at the Apple IIgs. And I've never actually written a 16-bit 2GS program. So I'm not going to talk in detail about how to actually use the Apple IIgs graphics modes, except for the memory model. So the 8-bit Apple II graphics modes are famously very complicated to work with. They have a nonlinear frame buffer, which means that the sequential scan lines on the screen are not sequential in memory. The way colors work on the 8-bit graphics modes is pretty hard to deal with. It's fundamentally a 1-bit color mode, and all the color actually comes from what's called artifact color, which essentially means the position of the pixels on the screen. And I gave an explanation of this last year at KFest. And for the double res graphics modes on the 128K Apple II line, adjacent pixel groups aren't even in the same memory bank. So this is all super annoying, especially to program with, to write applications that use it. And fortunately, the 2GS made things a lot better for graphics. So it added what's called super high-res graphics. And the memory layout of super high-res is much simpler. Firstly, everything is linear in memory, so sequential horizontal lines on the screen are actually sequential in memory. Within each scan line, we have 160 bytes of pixel data, and that's 1280 bits per line. And this pixel data is interpreted according to two auxiliary tables in memory. The first is called the Scanline control byte. And each scanline has one of these Scanline control bytes associated to it. And this selects which of the 16 color palettes to use for this line. And it tells how to interpret the pixel data for the line. So in more detail, the Scanline control byte directs the 2GS whether to display this line in 320 or 640 pixel resolution. There's an ability to generate an interrupt when the line is redrawn, and this is useful for things like animation, so you can update the graphics display without having tearing from racing the beam. There's something called fill mode, which is supported in 320 mode, which means that the zero color is special, and it means take the color for this pixel from the pixel to the left. And this is sometimes apparently useful, from what I understand, not as useful as you might think. And finally, it selects which of the 16 color palettes should be used to provide the pixel colors for this line. So we can see there's already a lot of flexibility here. There's not just such a thing as 320 by 200 mode and 640 by 200 mode, because we can mix and match the resolution on a line-by-line basis. And we can also select which of the 16 color palettes to use on a line-by-line basis. One of the tricks that was discovered fairly early on is that you can even update these color palette mappings as the image is being drawn. This is what's called 3200 mode, because if we're updating the color palette on every line, we have up to 200 effective palettes, which gives us a total of 3200 colors. So apart from the pixel data and the Scanline control byte, the third memory table we have is the color palettes. So there are 16 of them, and each of these contains 16 entries of 16 bits each. And those 16-bit values, well, 4 of the bits are unused, but then the remaining 12 encode the RGB value for that particular color. And so this is why we have 2 to the 12 or 4096 possible colors for each of the palette entries. So let's look at how we can then map the pixels to colors in 320 mode. Each scanline has a total of 1280 bits, and in 320 mode, these are interpreted as 320 4-bit values. So each pixel is obtained by successive 4 bits in this pixel line, and those 4-bit values give a total of 16 possible indexes into the palette table that the SCB selected for this line. That means that for each of these 320 pixels, we have 16 possible colors, and these are chosen independently from this particular palette. So here's a diagram showing this in practice. So these are the pixel bits in the pixel table, and they're grouped into 4. So the 0 pixel is given by the first 4 bits, and here I've shown the value 0110 in binary, which is 6, and that means that this pixel is rendered with the RGB value coming from entry 6 in the palette table. So in 640 mode, the scanline is a bit more complex. So here, the color of each pixel is given by a 2-bit value instead of a 4-bit value, and that means that there are 4 choices of color for each pixel. Here, the 16 entry palette table is reinterpreted as 4 subpalettes, each of 4 colors. And each of these 640 pixels is mapped to one of these 4 subpalettes according to its X coordinate, so X mod 4 essentially. So this means that we still have 16 distinct colors per scanline, but each pixel only has a choice of 4 colors, depending on its X position. So here's a diagram showing that. So again, we have the pixel bits, but now they're grouped into pairs, and each of these 2-bit values is indexed into a subpalette within our 16 entry palette table. So for X values 0 mod 4, we're limited to this particular palette here. And so here in our example, we've chosen entry 3. And similarly for the next pixel, that's chosen from the B subpalette here. And so these 4 subpalettes are striped vertically across the screen, A, B, C, D, A, B, C, D. So I'm not going to talk more about 640 mode because it's more complicated, and I didn't look into image conversions in that mode yet. But let's look at converting an image from a modern machine, which is typically going to be a 24-bit RGB image, to be able to display in 320 by 200 mode on the 2GS. So the first thing we have to do is to downscale the image to the right resolution, and that's straightforward. But then there are 2 hard problems we need to figure out. Firstly, for each scanline in our image, we need to somehow select which of our 16 color palettes we want to use for that scanline. And then for each of those palettes, we need to somehow pick the 16 12-bit RGB values that we should use to best represent those scanlines in the source image. So there's a lot of steps I'm omitting and a lot of details here to get this to work well. But those are the 2 core problems that we have to solve: mapping the scanlines to palettes and then choosing the color values for each of those palettes. So let's look at the first one. So the problem here is we only have 16 palettes to choose from, and we need to cover all 200 scanlines in the image. So how do we decide which palette should we use for a given scanline? The simplest thing we can do is just to use a single palette for the entire image. And this is what some previous image converters did. And that's a computationally simple approach to take, but it obviously gives up on a lot of potential because we're limiting ourselves to only 16 colors for the entire image out of this theoretical maximum of 256. So the next simplest thing we could do would be to use a brute force approach, where we look at all the possibilities of how we could do the mapping and then pick the best one by some metric. And so in my past work applying modern computing hardware to optimize 8-bit Apple II graphics and sound, I've got an awful lot of mileage from this approach, which is a testament really to the the power of modern hardware compared to the scale of the problem that it's solving. In other words, the 8-bit systems are usually simple enough in their degrees of freedom that doing a brute force approach is computationally feasible. But let's see how that works here. So each scanline has possible 16 choices of palette, and there's 200 scanlines. Yeah, so we're going to have to find something smarter here. So if the brute force approach isn't going to work, we need to look for some heuristics that's going to simplify the problem space. So one observation we can make is that typically an image is going to have similar colors on neighboring lines. So if you imagine, for example, a landscape image, then we're going to have a region of sky where it's probably going to be a blue color, and then we're going to have a region of land at the bottom, and somewhere in the middle that's going to change, but successive lines are going to have very similar colors to them. So one thing we could do is to assign each color palette to a contiguous range of lines in the source image. So something like this, for example, where we have, let's say, lines 0 through 19 mapped to palette 0, and then 20 through 39 to palette 1, and so on. And this approach can work reasonably well, especially if you tune these boundaries to match the particular features of the image you're trying to reproduce. But it tends to produce banding at these boundaries here, and that's because the different palettes are going to have different colors in them. If they were exactly the same colors, we'd just use a single palette, and you tend to notice that difference visually. So after a lot of experimentation, this is the approach that I landed on, sort of iterative approach to producing the image. So to begin with, we need to pick some guess for how we might map the scan lines to palettes. And something that turns out to work pretty well is to use sequential palette ranges, but actually to make them overlap a little bit. So we map an overlapping sequence of scan lines to palettes. And this tends to smooth out some of the banding effects that I talked about. So secondly, we need to somehow pick the best color palettes for this particular mapping, and I'll hand over that for now. But then supposing we've done that, then what we can do is to update the mapping of scan lines to palettes by picking the best palette for each scan line. So in other words, now that we've picked our color palettes, we might find that one of the other 15 of these palettes might be a better fit than the one we chose previously. And so we can update our mapping and then repeat. We can refit the color palettes using the new mapping and so on. And if we're evaluating our progress using some quality metric, then we can tell, is the new image better than the last one? And if so, we can keep iterating until we hit some limit where we no longer see any improvements. This takes care of the first of these problems of scan lines to palettes. We just need to figure out now how to choose the best palette for a set of scan lines. So now for each of the 16 color palettes, we've chosen which of the 200 scan lines in our image we want to use for that palette. We can take the set of pixels from those lines and treating them as 24-bit RGB values. This gives us sort of a cloud of pixels in this RGB color space. And now we need to choose 16 RGB values to use for our palette. And furthermore, these need to be 12-bit RGB values, not 24. So we can use here the fact that 12-bit RGB is a subset of 24-bit. For example, if we have a 12-bit value, which is given by these 3 nibbles ABC, then we can extend that to a 24-bit value by just repeating things A, B, B, C, C. And here we have to be careful about the exact color spaces we're using to make sure that we're using the right mappings. But once we've taken that into account, then we can embed the Apple IIgs color space inside a 24-bit one. And so now we can rephrase the problem that we want to pick the 16 points in this 12-bit subspace that best characterize a cloud of 24-bit pixels. So what does that mean? Here's a picture. So what I've shown here is I've taken a set of points from some image, and then I've graphed them as in three-dimensional RGB space. So the coordinate axes are given by the red, green, and blue color values. And we can see there's some structure here. There's clusterings of different colors. And our problem is we want to pick 16 points in this color space that best characterize that cloud of pixels. And furthermore, we want them to be 12-bit values. So we can think of that as being constrained to lie on these grid lines. So not just an arbitrary point, but something which is constrained to lie on this subgrid. So that still seems like a pretty complicated problem. So how can we solve that? Well, the approach that I found to work was to use a technique from machine learning, something called k-means clustering. And well, I won't go into the details of the algorithm, but it's relatively straightforward. But it's essentially the problem that we have. Suppose we have some number of points. We want to partition them into a smaller number of clusters. Here, 16 clusters, such that each cluster is best characterizing the points, which means minimizing some total squared distance metric. And the animation here shows that a simplified version here, where suppose we wanted to pick 3 values that best describe this set of points. It's an iterative approach for estimating what those characteristic points are. So this approach turns out to work pretty well. So here's an example of an image converted using this approach. The source image is on the left, and then the right-hand side is showing a 320 by 200 Apple IIgs super high-res image using this algorithm. So here's an animation showing the progress of image quality through successive iterations of the algorithm. And so you can see there's the appearance of some artifacting in intermediate stages, but the end result is fairly good. I'll come back to some of these image artifacts later when I talk about the limitations that the algorithm has. Here's another example. Again, the quality is fairly good, but you can see if you look carefully in the background, there's some artifacting that happens where this is the limitations of only having 16 color palettes to work with. Sometimes the best we can do is to sort of dither the color palettes back and forth on successive lines, where we alternate palette 1, 2, 1, 2, or something like that. And you can see sort of these horizontal striping that happens there. This is my favorite of the 3 images. I think this one turned out pretty well. But if you look closely on the legs, for example, you can also still see some of this banding that limits the quality. Talking more about some of the limitations of the approach. Firstly, the quality metric that I'm using, which is just some total squared error metric, doesn't always strictly match how the human eye sees the image. And so sometimes you might find that there's an image which is technically lower error according to this metric, but it has some sort of visual features or artifacts that make it less pleasing. And so you might find, for example, that an intermediate step in the processing actually has looks better to the eye. One other feature is that it's not a deterministic algorithm, which means that if you run it again, you might get slightly different results. And this is something you can actually make use of if the image quality isn't what you want. Sometimes if you run it again, you'll get something better. We've seen some examples of some of the artifacting that can happen where we dither the palettes across successive lines, and this can be sometimes noticeable. One thing that you find in practice is that in most cases, the images aren't able to make use of the full 256 number of possible colors. And usually you can get about half of that. And that's just because we have this fairly major constraint that we don't have 256 independently choosable colors. We have 16 per line, and then a choice of 16 palettes for each line. And so you'll often need to pick the same color in multiple palettes in order to match the image. So everything I've talked about here has been in 320 mode. It should be possible to extend this to the other 2GS graphics modes. Supporting 3200 mode should be fairly straightforward because it's a much less highly constrained problem. If you're able to effectively choose a unique palette for each line, then we don't have to worry about one of the hard steps that we had to deal with. And this should avoid most of the problems we see in the image banding as well. So this one should be a fairly straightforward extension. Dealing with 640 mode, it seems more challenging because there's the extra optimization constraints from the fact that we have 4 sub-palettes that we have to choose within each of the 16 palettes. And so that's a more highly constrained problem, and it makes it harder to produce images of similar quality. The flip side of that is that this might potentially be an opportunity, given the right algorithm. If you're able to solve the optimization problem effectively, then perhaps you can get much better image quality than people are used to. But so if you want to look at the state of the art of 640 mode image conversions, then FatDog on the Apple II Slack does amazing stuff with 640 mode image conversions. So I'd invite you to check that out. So here's a link to the source code if you want to play with this yourself or look at some other image conversions that I've got up there. So thanks very much, and I'll be happy to answer any questions. Yeah, happy to follow up later. Otherwise, oh, sorry, there's a couple in the Q&A. Can I post the GitHub link? Yeah, certainly. I'll post that in the Discord in a few seconds. Can I explain again how I avoid banding? So this is basically a way. So the algorithm, it starts out by assuming, well, what if we start by assigning sequential image lines to the same palette? But then once it's fit the palette, it might say, well, actually, lines 2, 3, and 7 better fit some other palette, and so that it ends up sort of interleaving them successively and then refitting with that new mapping. And that tends to smooth out the banding effects that you see, because it will sort of naturally try and smooth away the discontinuities that you have if you just have sort of one palette than the next. So the cost of that is that sometimes the best you can do is that you have to sort of interleave, swap palettes back and forth, and then you see sort of one color, slightly different color, one color, slightly different color, as like single line banding in the image. But you at least avoid typically the big sort of, you know, patch of light, patch of dark that you can get if you just sort of do the simple approach. If that didn't make sense, then we can follow up on the Discord. I can point to some images that sort of show the features I'm talking about. Had a question about a program called XV on Unix. I haven't heard of that, so it's possible they independently did the same thing. But yeah, I have to look into that and see what they did.
Hey, this is Dave Slaughter at Rockhurst. I was taking a look at your GitHub page, and I want to thank you for making this as easy as possible for people to adopt. I see that you have the Python requirements.txt as well as usage and installation instructions. So thank you for being very thorough about that.
You're welcome. Yeah, that some of that was fairly new. I think it was a little bit tricky in the old version to get the dependencies installed, but yeah, I certainly would like it to be as easy as possible to use. So if anyone has any trouble with that, then just drop me a line.